Starting the recording. Good evening, everyone, and welcome back to FractalU.com. Thank you for joining us. Our super exciting guest tonight is Jean-Paul Biberian, a leading cold fusion physicist from South France. Welcome, Jean-Paul. Say hi, everybody.
Hello.
Glad you're here. So nice of you to take the time to share with us tonight, Jean-Paul. Jean-Paul has taken special efforts to make the physics and science of fusion available to the general public in an empowering way. We'll put his websites, cryofusion.org and jeanpaulbiberian.net. His websites we will list here, and you'll see more about that. I'm going to do just a couple of minutes intro and then turn it entirely over to Jean-Paul. Just a procedural note here for FractalU.com that Alan Green's scheduled presentation on Shakespeare, D, and physics constants, scheduled for May 6th, is rescheduled due to his medical issue, and instead we will have Teresa Burns again with Alan and myself, and we'll be presenting on May 6th more about plasma projection alphabets and about history of alchemy science. And so speaking of alchemy science, I'd like to make a little parallel to what Jean-Paul is talking about tonight. You know, Jean-Paul's field is professional physics, clearly, and for Jean-Paul, if it's not measurable, you really can't talk about it, and I support that view, actually. And Jean-Paul has a particular expertise in that area, and his expertise actually is calorimetry. The point I'd like to make is that there are many names for implosive charge collapse or non-destructive charge collapse, which incidentally was Einstein's name for the principle behind gravity, was infinite non-destructive charge collapse. And one of the names for that is isotope transition, which is when not only do the electron shells collapse between shells, which is classical chemistry, but when the actual nuclear hadron, the protons and neutrons, component collapse and change state, as it were. So when things start happening at the nuclear level, that's introduces the subject of fusion, which Jean-Paul will be speaking tonight. The point is that whether you call it isotope transition or non-destructive charge collapse or cold fusion or alchemy, alchem, the principle is essentially the same, which is perfecting compression and therefore gaining energy from compression. And you know, the theme of so many of our courses is that a fractality of field, as it were, is a mechanism to allow charge to condense, collapse, implode, as we say, negentropically. And negentropy, or a form of self-organization from charge collapse, is one way of talking about a fusion reaction and what Jean-Paul measures, because what Jean-Paul obviously is looking for is when a fusion reaction occurs in such a way that there is excess energy, that heat is released, which is anomalous, which is, to say, not accounted for by classical electron chemistry. So, you know, although alchemy is still probably a controversial subject among physicists like Jean-Paul, there are actually many great physicists of history were actually alchemists, obviously. But the core physics principle, which is that getting charge to implode and transmute and change even at the atomic level, is the essence of both alchemy and fusion, ultimately. And physics has a more disciplined way of talking about alchemy today, as in isotope transitions and charge collapse. We actually have some series of new equations predicting specific frequencies and temperatures to catalyze charge collapse and isotope transitions. So really, in a way, in new physics, alchemy is becoming commercial physics. And indeed, Jean-Paul's work now, since he's retired from Marseille University Physics Department, Jean-Paul is doing commercial consulting in fusion physics, cold fusion physics, for major automotive companies who are obviously interested in this and seriously take it seriously enough to support it. And Jean-Paul has done so much to support cold fusion research around the world. He's sponsored international university conferences on cold fusion. Jean-Paul's new book on cold fusion, the introduction, I believe, is written by Pons of Pons and Fleischmann, who did the famous original research here. Jean-Paul knows all these people personally. It's really a wonderful thing. So we're just making the point that as we talk about the mysteries of alchemy and the sort of spiritual implications, the hard physics, which boils down to measurement, is something we respect totally. And as we try to see those pure principles, we're delighted that Jean-Paul is with us and taking time to bring this to a layman's conversation about current latest developments in cold fusion research by measurement. And just one last thought before I turn this over to Jean-Paul. You could say, why do you call this physics of fusion, why do you call it cold? Which is really the right question. And I'm sure Jean-Paul will comment, which is fun. But just to say that normally the fusion reactions, for example, when two hydrogen atoms fuse to make helium in the heart of the sun, normally conventional physics requires a huge and vast amount of heat is required to initiate that kind of fusion. And that's been the challenge of fusion energy research so far, is how do you get that much heat focused so you're hotter than the sun to make hot fusion possible? Well, cold fusion means that if you get either the wave mechanic or the electron shell symmetry correct, then you can cause these magical energy producing fusion reactions without adding that huge amount of heat, and that's why it's called cold fusion. It isn't magical, actually. It's understandable now in even conventional physics. And that's why Jean-Paul is here to share with us. So thank you, Jean-Paul. I turn it all over to you. Here you go. Thank you, sir.
Thank you, Dan, for the introduction. Let me see first about cold and hot. Cold and hot is like poor and rich. It's very relative, depends where you are in the scale. In this case, cold is related to the hot fusion, where you're talking about millions of degrees of temperature. So cold fusion is at close to room temperature. That's why we call it cold. Anyway, let me. By the way, you talked about transmutation. Maybe one day you should invite me to give another talk about transmutation, because there are many experiments that have shown transmutation of elements besides alchemy. So maybe one day we'll do another talk for that. if you
So your expertise is in transmutation as well as fusion, which is more related to alchemy. Good point. Thank you, Jean.
Okay, next time. Anyway, my field is, I am an engineer and I have a PhD in physics, and I worked for 42 years at the university in Marseille, and I also had I was a postdoc at the University of Berkeley in California. I went there twice, spent quite a few years there. So I traveled a lot, but I continued working. In my field was surface science. I was just looking at how atoms at the surface of a metal behave. So it's very interesting. I like this field. But in 1989, something happened very important. There was this announcement 29 years ago by two professors, Stanley Pons from the University of Utah and Martin Fleischmann from the University of Southampton in England, about the discovery of cold fusion. Let's see. Now, this is a very controversial field. I will tell you why it is so controversial. But anyway, let me go to the next slide. So this is a summary of what I'm going to tell you about. Before 1989, there were some discussions about strange effects in materials loaded with deuterium. Then I will tell you a story about the story of cold fusion, the experiment by Pons and Fleischmann, the excess heat, the measurement of helium, particles, transmutation, experiments in gas phase, what the industry is doing, the theories, the conclusion. I'm not going to spend much time on theories because I'm not a theoretician, and at this point, no theory explains the whole thing anyway. So not much. It's interesting, but too soon for a real demonstration, a real good theory. Even though I think there are many people think they have the right theory somewhere. What happened before Pons and Fleischmann? That was just before Pons and Fleischmann. in 1986 and 1980, there were two physicists. I mean, the lead scientist was Gibson. Unfortunately, he died a few years ago. They showed that there was production of neutrons when you force or apply a force on heavy water ice or on LID. Interesting, because normally you don't get neutrons like that, you know. And that was published in a Russian journal. And later on, also they showed there was a paper in Nature, 1989, showing there was production of neutrons when the powders of titanium deuteride are submitted to mechanical vibrations. I mean, that's interesting, isn't it? You vibrate a titanium deuteride and you get neutrons, you know. So it's not like you should do that with conventional nuclear science. You never do that. But they have shown that it was possible. That was published in Nature, so that was important. But what happened? On March 23, 1989, there was a press conference in Utah, at the University of Utah, the Salt Lake City University, press conference, and that press conference, they announced that they had discovered a way of making nuclear reactions in a test tube. I mean, everybody knows that you cannot make nuclear reactions in a test tube. You need to have high energies, or you have radioactive materials, but you cannot do that in a test tube. So what happened? Immediately, all the scientists that had they were using electrochemistry. I'll show you on the next slide so you will understand what it is. The original experiment. Oh, by the way, on the right side, you have Martin Fleischmann, who died in 2012. And on the left side, you have Stanley Pons, who lives now in France, the south of France. I had a chance to be a friend of him, so I see him once every 2 years maybe, or we chat if necessary on the phone. But he's a very great scientist. I really appreciate what he's doing and the way he behaves. Anyway, here is the experiment. I will zoom in since I can zoom. Good. Okay, this is a cell. You see, this is a double wall cell with vacuum in between, just like this is vacuum, just like in a DWAR, but it's all glass, so it's transparent to light. And the cathode is at the bottom, and this is the anode. You can see it here. It's a platinum wire. The cathode is palladium, and palladium is known to accept a lot of hydrogen. It loads very easily hydrogen. I mean, at room temperature, at the atmospheric pressure, in the good conditions, you get a ratio of 0.7 hydrogen per palladium atoms. If you want to go higher in loading, you have to go to much higher pressures. But by electrochemistry, the idea was to load more hydrogen in the palladium because you get what's called overpotential. I mean, if you have two metal electrodes, like in a battery, you have voltage between the two of them. Now, if you put hydrogen in the palladium, then the voltage changes. And the voltage is associated with the equivalent of an external pressure. It's called a fugacity. The fugacity is equivalent to a pressure, as if there was very high external pressure. So according to Pons and Fleischmann, when they studied this experiment, they decided to load a lot of hydrogen inside to reach a huge pressure, astronomical pressures, so that the idea was that if you put deuterium instead of putting hydrogen, then you will have fusion of the deuterium together due to the pressure and not to the temperature. Normally, if you look at what they are doing in France with the ITER project, they want to go to 150 million degrees, high temperature and high density of hydrogen in the system. Here, they lower the temperature, but they increase the pressure. That was their basic idea. That's why they studied this all the world. So, at the top, the whole thing is in a constant temperature bath, And by measuring the temperature inside the cell and in the bath, you know the Boltzmann power to the forced temperature law, and then you know that you can calculate the energy produced. This is a very simple calorimeter, but very accurate. If you do things correctly with good precision, you can get the precision better than 1%. So that was their original experiment. So let's be back to the history. Yeah.
Jean-Paul?
Yes.
Could you just talk about the palladium for just a minute for fun? You know, I knew that Jim Patterson, who made the first cold fusion palladium beads, and you remember the story was that because he couldn't replicate the unique quality of the first batch of palladium beads, they couldn't replicate. So there was something about the palladium, and even Valerie pointed out it felt cold in your hand. Was that story related here? The palladium beads had to be unique, or?
Well, palladium. Well, let's say palladium beads of potassium. Let's talk about that later. But even with the Pons and Flashman experiment, the quality of the palladium is very important. So you have to understand how it happens to have hydrogen inside the palladium. So hydrogen, normally in the gas phase, hydrogen is a molecule. But hydrogen cannot go inside the palladium if it is a molecule. It has to be an atom. But in doing electrolysis, you dissociate the water molecule. So if you have heavy water, you dissociate and you have D plus ions that are at the surface of the palladium. And they can enter the palladium. But as you increase the current, if you increase the time for the experiment, as long as time is passing by, you load more and more palladium, hydrogen or deuterium inside the palladium. But as it is as if the pressure inside the palladium was very high due to the hydrogen. So if you have tiny breaks, nano breaks at the surface of the material, then the hydrogen will go out, as if you were trying to inflate a tire with a hole in it. So you put more and more air inside your tire, but you never inflate it because there are holes in it. So in order to work, you need a good quality palladium that will accept the hydrogen but not let it go out. So it can go in, not out. So the quality, the metallurgical quality is important.
Because the sort of fun story at the time was that there was a certain kind of quote-unquote alchemy required for the proper preparation of the palladium. I just would mention for fun for our group here that classically, if you believe occult chemistry or even conventional chemistry, the physics is the outer DF subshell of palladium could be regarded as dodecahedral. And I was the one regarding hydrogen who proved that the hydrogen radii were ratios of golden mean, meaning pent also. So there is probably some importance here that both the hydrogen and the palladium had some pent dodecahedral golden ratio phase conjugate qualities. That may be a speculation, but I think that's what makes this in a way fun for me. But go ahead, Jean-Paul.
Okay.
Please continue.
I understand. The point is that this palladium was made by Johnson Matthey, and they call it Class A type of material. But later on, Johnson Matthey changed their procedure of manufacturing their palladium, and the new palladium didn't work. So what happened at that time in 1989, March 29, a lot of scientists who had a little bit of palladium, a little bit of platinum, heavy water, tried to do the experiment. Most of them failed, as usual in science. You know, it's hard to make an experiment in a couple of weeks. It takes time to repeat an experiment. So most of them failed. Some succeeded. And the theoretician said it's impossible. You cannot fuse two deuterium atoms like that. It's impossible because they're too far away. In order to have tunneling, you have to, the chances of getting tunneling is less than 1 part in trillions of years, something like that. You know, it's impossible. So there was a lot of controversy, discussions, and there was a panel organized. I mean, I cannot go too much into the details, but finally the jury was out and they said cold fusion doesn't work. Basically, that's what happened. and it was forbidden to work in cold fusion everywhere in the world, not only in the US, but everywhere else. So those people who had started just stopped. Most of them stopped. Some continued, obviously, because they wanted to, because they had seen something interesting, so they wanted to continue the work. Anyway, so that's how cold fusion has become like something like underground research and not official research. It's not accepted in scientific journals. It's hard to publish because they don't want to accept it.
It's very cool that if hydrogen is kind of fractal or phase conjugate, that it's generally hydrogen that's involved in these fusion reactions, even though, as you say, it's so apart in the atomic table from the palladium in this case, or in your current work, similar to Rossi, it's hydrogen and nickel, isn't it? So in both cases, you're squeezing something that may be phase conjugate into. There's an interesting parallel.
Well, the reason why they choose palladium was that palladium is the noble metal. That means it doesn't get oxidized or very, very lightly oxidized. So that way you can easily enter hydrogen inside the palladium. If you take nickel, nickel is not a good candidate because there's always an oxide at the surface of the nickel. So you have to remove the oxide in order to put the hydrogen in it first. So it's more complicated. And normally you have to go to 6,000 atmosphere to get hydrogen inside nickel. Whereas with palladium, you get it at the atmospheric pressure. So that was a good choice to do this kind of experiment using palladium. Anyway, well, this is a picture of what's happening inside the cell. You see the bubbles coming from due to the hydrogen and oxygen being produced. And the idea was that there is some steering of the water because the bubbles go up, so the water goes down, and so the temperature becomes uniform inside the cell. So just by measuring one temperature inside the cell, you have a good idea of the temperature, the whole temperature. They made some measurements with several thermistors to measure temperature at different levels and showed that it's very uniform. So they use a very simple device to do their experiments. This is something people should know. When you make a discovery, you have to make your own instrument. You cannot buy it on the shelf, somewhere. It doesn't exist. You have to make it. So that's what they did. So what was the situation? Yeah.
Jean-Paul, Lisa is just suggesting if you could talk a little slower, because the mic is just a little bit slower. Okay. Sorry. Go ahead.
I'm sorry. I'm so enthusiastic that I can talk too slowly. I will try my best. All right. In fusion reactions with deuterium, you have three possible reactions. D plus D will produce tritium plus a proton with an energy of 4 mega electron volts. D plus D might produce helium-3 plus a neutron and 3.3 mega electron volts. And these two reactions are about 50-50. So that makes sense to have both of them in a reaction. The last reaction will be D plus D producing helium-4 and a gamma ray. And this one is a more energetic reaction with almost 24 mega electron volts. But chances are very low, 10 to the minus 7. So most of the time you never get these gamma rays and the helium-4. So what people said, you should have a lot of neutrons. If you have excess heat, then you should have neutrons. And if you have neutrons, you should be dead, by the way, because there's so many neutrons. So that were the three reactions, and that's not what they have observed. So they call it the three miracles. Okay. If the D plus D reaction occurs, then there are three major theoretical problems. One is called the Coulomb Barrier, because as you know, if you have two positive ions, they will not attract, they will repulse. So they cannot get close enough to fuse. So that's the one miracle. How do you overcome the Coulomb Barrier? You need to bring them closer to each other. Now, if you, for some reason, your miracle is accomplished, you never know. No, there is another problem. You should see neutrons, but there is no neutrons, or very few. So that's another miracle. Why no neutrons? So you would say, well, because maybe the third reaction is occurring. The third reaction has no neutrons, produces helium-4, but produces also gamma rays. But there's very few gamma rays, or no gamma rays, really. So you have three miracles in order to explain the experiment. Three miracles is a bit too much. One is already difficult to achieve, but three, it's a lot. That was problems raised by the theoreticians.
Interestingly, Jean-Paul, in our current work, we're working on new equations for the gravitational constant as implosive charge collapse. And the key variable is the Coulomb constant, which is related to charge collapse. So if we understand charge collapse accurately with Coulomb, we may see that it's not just the key to fusion, but centripetal forces in general.
So anyway, these people found excess heat. So what can you say? In science, experiments are more important than theories. If your theory doesn't fit the experiment, you have to change theory. You can't change the results of the experiment. You have to change the theory. But people are very reluctant to do that, So McCubry from SRI, Stanford Research Institute in California, made a very interesting experiment. He did compare, he had his own calorimeter. I won't go into the details of the calorimetry, but he compared an experiment with light water in blue and here in blue, and one with heavy water in red. Now, and what you see on the x-axis is the current density. The current density increases, and with light water, there's no effect on the current density, it's zero. Whereas with a heavy water, there's a threshold, and then you see almost a linear increase in the excess heat. It's not much. We are talking about 0.5 watts, 0.6 watt up there. But it's very significant because you see it's way above the error bars. So this is real. I mean, McCubry was working on loading of hydrogen in palladium before cold fusion. So when cold fusion occurred, he was ready to go directly and do experiments. And also we had the chance to know Martin Fleischmann because he worked with him earlier in England. So they chat and discussed, they gave him all the details of the experiment, so he did the experiment. So this is a good proof that heavy water does something and not light water. Now there is a Japanese scientist called Arata. Arata is a very good scientist. Actually, he got recently, I'm talking about 20 years ago almost now, at least 15 years ago, he got the gold medal of the emperor because he was a very good scientist who made a lot of work for the government. And he had a good idea. What he did, he took a palladium cathode, he drilled a hole inside the cathode and filled it with palladium powder, sealed it, and he put it in his calorimeter. This is the cathode, this is the anode, and he has a way of measuring the excess heat by measuring the temperature by water flow. He's flowing cold water in the system and getting hot water, measuring delta T and the flow rate. You can calculate the number of calories produced by the calorimeter. So this is a very smart experiment because in this experiment, when you do that, you dissociate hydrogen at the D2O molecule. So D plus enters the palladium. I will zoom in here. So it's good to have zoom here. Okay, let me zoom in a bit more so it's even better. Okay, you dissociate your H plus or D plus is produced at the surface here, diffuse inside the bulk of the tube, then enters the powder. Palladium black. This is powder, palladium powder. So what happens? As time goes on, slowly, the pressure of deuterium increases inside the tube and inside this powder. And maybe you're not aware of, but if you talk about powders, the properties of powder is different from the properties of the bulk material, because there are a lot of surface defects and the arrangement of the atoms are different in a powder than in a solid material. Anyway, this is his experiment. What he did that he put two experiments in parallel, one with light water and one with heavy water. It was running the same current, so it was just comparing the two cells. What is observed is here. This is time in hours. If you look at it, it's a large number. I will zoom in so you can see it better, maybe. Good. 2,200 hours. That's almost 3 months. So you run the experiment for 3 months, and with the light water one, there is no excesses at all. With the heavy water experiment, for quite a few weeks, there is nothing, and then the excesses appears. It goes very high. Here at 24 watts. It's a lot of energy. You will say, why did it stop here when it was working so well? You know, why do you stop when it's working well? What's happening is that the cell exploded because the pressure inside the cell increases so much because you're putting more and more hydrogen that the cell exploded. So you had to stop. It just stopped by itself, you know.
So it actually blew up, huh? But
yeah,
But Jean-Paul, so if deuterium heavy water means you got an extra hydrogen that's more available, and therefore, is that the hypothesis here?
No, this is due to the fact that you have now deuterium gas or deuterium atoms, not gas, atoms going directly inside this powder of palladium. And this is more reactive because it's powder. And deuterium can fuse. D and D can fuse, whereas H and H is difficult to fuse. D and D might produce helium-4.
But deuterium is basically two hydrogens, isn't it?
No, it's a proton and a neutron. Whereas
I see.
That's why. Proton and neutron.
So it's actually a free neutron as opposed to another proton. That's the point.
So deuterium is a proton and a neutron together. The nucleus of D is proton and neutron, whereas the nucleus of hydrogen is only a proton.
And somehow that creates the availability to react even at a nuclear level, presumably.
Then now, we don't know what's happening because nobody knows really what's going on, but possibly the two deuterium plus neutron and proton fuse together with another one and produces helium-4. Helium-4 is 2 neutrons and 2 protons. That's what it is. So that's the guess, but we are not sure. That's what we measure. Now the proof would be to see helium-4. Oh, another thing. Letts and Cravens are two scientists, physicists in the US, and they did something interesting. They had a calorimeter with palladium, and the palladium was working fine, was producing excess heat. But at one point they shed a light, red laser, you know, the pointer type of laser. And they saw immediately an excess heat increase due to the laser. So the light is doing something. But that means excitation of the surface of the material is having some effect. That's the proof that you can put it on and off by turning on and off the laser. And actually, Letts and Craven did something even better. They took two lasers and did a beating with the two frequencies. They took the two red lasers at almost the same frequency, but by changing slightly the frequency of one of the lasers, they could produce a low frequency signal in the terahertz range. And what you see, that this is the excess heat versus frequency, and you see these peaks. I mean, scientists love peaks, you know. When you have something like that, you can do some calculations after that because you have numbers. You can see that.
Yes, actually, yeah. Jean-Paul, we obviously would have some detailed equations to predict which frequency should be more conjugate. So we should do that comparison. That's exciting.
Yeah, you have the numbers here.
Yes.
Can you read them? No, maybe you can read them.
Yeah, actually,
Oh, yes, here. I can give you the real number. Yeah, this is completely. The numbers are
yeah,
not
I'd love
correct.
to check that. Love to check that. Thank you. Super.
Okay, sure. That's very interesting because you have the frequencies. That's what you want. Frequencies. They're peaks. Maybe
Exactly.
as people think it's associated with phonons of the surface of the material. Maybe not. I don't know. That's what we think. Now, there is a guy in the US who has this idea of making super waves. Super waves are waves plus another wave on top of it is you are adding square sine squares and another one. So you see this oscillation like that. It's always positive, but as if you were knocking slowly and then harder and faster, different frequencies altogether. And they try to do something with that in doing electrochemistry. That was the experiment was made in Israel years ago. And what they
I mean,
observed,
Jean-Paul, the theory is that from phase conjugation actually creates the perfect superwave, even as harmonic inclusiveness predicts fractality in Hart harmonics, for example. The graph of perfect Hart harmonics is that kind of graph with harmonic inclusiveness perfected, which is actually kind of implosive potentially if the recursion becomes fractal, even in frequency signature.
so this is exactly what you need. Then. You have the
Yeah.
numbers there. So what happened? Here the input power in black, and here the output power. Look at that. It was so hot that the whole thing melted inside and stopped after 17 hours. But for 17 hours, there was a lot of excess heat. Unfortunately, they never could reproduce this experiment. Everything melted inside, but they couldn't reproduce it.
Oh, because we should be able to consult with them and perfect that frequency signature.
Maybe. If you can tell me the frequency, we can do it together.
Cool. Let's do it.
Yeah. It's just electrochemistry. The current is fluctuating that way. We know that in cold fusion, you need to have always some kind of dynamics, you know. If things are stable, nothing happens, you know. You need to shake it somehow, either with the pressure, with the current, with the magnetic field, with the laser, with something. You have to shake it, otherwise it won't work. This is, they put an average 20 watts. They put 0.74 watts and got 20 watts, the ratio of 25. This is huge, you know. We love to have that every day.
That's fabulous. That's really fabulous.
At MIT, there is this guy called Mitchell Schwartz, and he has developed, he called it a nano. The nano is made of, it's about the size of a resistor, you know, electronic resistor. And inside that, he has a powder of zirconium oxide and palladium, nanoparticles of palladium. And he loads it with deuterium, passes a current through it, and then you get excess heat. He has made demonstrations of that. Now he's selling it. If people want to buy one, you can buy one. So this is work. He has shown, look at that. The control was in blue, the experiment is in red. Look at that, excess heat. So it's working very well. And is repeatable, can reproduce anytime. Now, let's see about particles. Helium, tritium, neutron, proton, X-rays, alpha particles. Helium-4. Arata, I was telling you that Arata did this double cathode, you know, with the powder inside. And he had attached a mass spectrometer to his cell. And what he did, if does the experiment with light water, he sees no deuterium peak, no helium peak. But if he does it with heavy water, you can see the helium peak and the deuterium peak. They are very close together because helium-4 is very close to deuterium. They're almost the same mass. And the difference is the 24 mega electron volt energy of binding the two deuterium together. So you need to have a good mass spectrometer to separate these two. But you can clearly see the helium-4 peak. I was telling you that the third reaction might occur, producing helium-4, but no gamma, but helium-4. That's what he saw. Makumri did the same thing. He measured the excess, the quantity of helium produced compared to the plotting against the energy produced, I'm sorry. So you get a pretty good linear curve, a line, and the energy is about 31 mega electron volt. I was telling you that the reaction should be 24, so you're getting 31, pretty much in the error bars. So that could be explained the reaction, D plus D producing helium-4, but no gammas. So something else is happening in the cell, but no gammas. Claytor at Los Alamos. Claytor was a scientist working at Los Alamos. So they know everything about measuring tritium. And he did experiments like discharges in deuterium gas with palladium electrodes, and he could measure tritium very clearly. He had a lot of experiments showing showing production of tritium. So we can make a little bit of tritium, but not much. It's very small quantities, actually. So we think the main reaction is production of helium, but there are also some other reactions. Neutrons. Jones did some experiments with a calorimeter with neutron detectors, and he could measure a few neutrons. But if you look at it, this is the background, this is the number of neutrons. But if you see the scale, it's only 10 neutrons. You cannot kill someone with that. But yes, certainly a little bit of neutrons above the background. But again, very, very small quantities of neutrons. Nothing compared to the energy released in the experiment. Alpha particles. There are many ways. There are many ways to measuring alpha particles, but one way is to use what they call a CR39. It's a piece of plastic. When a neutron goes through the plastic, you make a tiny hole in it, and then you etch it in a basics solution, and then you increase the size of the hole, and you can see it with a microscope. Anyway, Fisher did some experiments. I will zoom in here. Well, okay. He was doing electrochemistry with the cathode and the anode here, and he did put some pieces of the CR39 to detect the neutron production. And what he saw, this is the holes due to neutrons. Look at all these holes. The good thing with that is with neutrons are hard to detect. There are all kinds of detectors, electronic detectors, but they are very sensitive to noise, electronic noise. Whereas a piece of plastic is not sensitive to electronic noise. So you can measure, you can see the amount of neutrons he has measured, but this is an accumulation. So the rate is very low, but accumulated, you see they are there, no doubt. You can see the alphas, you can see the neutrons, you can see both. But you have to analyze in detail the shape of the holes to find out if it is an alpha particle or if it is a neutron. Now, transmutations, you might be interested by that. Mitsubishi Heavy Industries in Japan did a lot of experiments in cold fusion, and they looked at something very important. They took a piece of palladium, 25 millimeter by 25 millimeter, one tenth of a millimeter thick, and they deposited 5 layers of calcium oxide and palladium, alternative layers. Calcium oxide, palladium, calcium oxide, palladium. And then they ended up with a thin film of 400 angstrom of palladium. On top of that, they deposited cesium. Cesium. They deposited a layer of cesium. They put it in the machine where on one side there was a high pressure of deuterium, on the other side there was vacuum. So they could pump deuterium through the foil. As I told you, palladium is very open to receiving deuterium or hydrogen. So if you pump it, it will go through, it will be pumped on the other side. That's a way to do hydrogen purifiers, by the way. So the deuterium is molecular. When you get to the surface, it dissociates, and then there are Ds. The Ds go through, reassociate at the surface, and comes out as D2 again. It's the permeation. So this is their experiment. It was a highly sophisticated experiment with a vacuum chamber where they could put the gas, the deuterium gas, the foil here. They had different techniques to analyze the surface called the X-ray photon spectroscopy, where you send an X-ray, we have an X-ray gun, and you analyze the photoelectrons that are emitted, and you can analyze the composition of the surface that way. So it's a complicated experiment, but what they saw is interesting. They saw that the cesium peak was decreasing with time, and at the same time, there was a new peak that appeared, called the praseodymium peak. So cesium was going down, praseodymium was going up. If you're familiar with the technique of X-ray photon X-ray.
I think we lost Jean-Paul for a moment there. Might be his connection. Sorry, folks. Let's just see if Jean-Paul's there.
Did I lose everyone?
Yes, are you back there, Jean-Paul?
Yeah, I'm back there. Okay, it's working now again. I don't know what happened.
It's probably a break in your internet. Turn on your camera again, that's all.
Oh, I see. Where is my camera?
In fact, I have to reset the controls. One moment. So I've put, yeah.
Can you see me?
Try restarting your camera, your webcam, Jean-Paul.
I see the webcam. It's not working on the screen. I tried it. It doesn't work. For some reason. Well, it's not very important to see my face. You have seen it enough, no?
Okay.
Okay, let's continue without the camera. I don't know what's happening. Why I don't have this is the camera. No.
Jean-Paul, just one quick comment, if I may, backing up just slightly, that the fact that no gamma rays were seen means basically that the nucleus really didn't fall apart very much, that it was a fairly coherent transmutation, right? Is that what no gamma rays mean?
Gamma, if you imagine two deuterium atoms colliding one against the other in vacuum, so you will fuse them and produce helium-4, but then you have a mass loss. You lose some of the mass of the system, so you have to transform the mass into energy somewhere. But because the two deuterium are going one against the other, the momentum will be zero. So you have to produce something that will take the energy away. But the only way in vacuum to do it is through a gamma ray. Whereas in a solid, there are other ways of producing this energy. You can use it as phonons. Probably you produce phonons in the lattice. Phonons are the vibrations of the lattice. So instead of having one big energy, you have chunks of small energies goes into the heat. That's why you produce heat and not gamma rays. Possibly, this is a possibility. Well, but we're not sure. This is a theory. Eh?
Yes, and the hypothesis is that the orderliness of the frequency signature in also, which of the energy input, also affects the orderliness of the frequency signature out, which is the heat output. And in both cases, if those harmonic series were more conjugate or fractal or recursive or golden ratio, the theory would be that you have a more orderly reaction. And that whole idea is being cold in the fusion.
Anyway, that's what's interesting here, that they have shown that you can transmute cesium into praseodymium. Now they did the same thing. Instead of putting cesium, they put strontium on the surface. And then, again, same thing. The strontium goes down and a new atom comes up at the surface called molybdenum. So they have seen transmutation of strontium into molybdenum. Interesting.
That's molybdenum.
Yeah, molybdenum. Yeah. The molybdenum has a number of isotopes. This is natural molybdenum. 1, 2, 3, 4, 5, 6, 7 isotopes, you see? However,
yes,
the molybdenum they have observed has only one isotope.
right.
So they have produced anomalous molybdenum.
It would be interesting to analyze the spectra and geometry of the isotope that was produced to see if it fit the conjugation theory. Also interesting.
Actually, this mass 96 is due to that. If you take strontium and you add 4 deuterium, strontium 88, then you produce molybdenum 96. If you take cesium 133, you add 4 deuterium, then you get praseodymium 141. So you see?
Right.
And then, yeah, due to the isotope at the beginning, you know.
Right.
Now, if you do the same thing with barium, then you produce samarium with 6 Ds. It's even worse. It's interesting. I mean, can you imagine fusing 4 Ds onto a strontium, 4 Ds into cesium, and 6 Ds into barium? But that's what they have observed. And actually,
yes,
in Japan, at the moment, they are working with cesium-137, which is radioactive, to destroy it.
and so if you count the number of hadrons, protons, and neutrons in versus out, the arithmetic has to add up, is what you're saying, which is great. But also, slight differences in that nuclear mass presumably predict the amount of anomalous heat output as well.
Absolutely. Yeah, this is fusion, so you have excess heat. But in that experiment, they never measured excess heat. They measured only the transmutation products. They were not capable of doing calorimetry. This was very small amount of materials being transformed.
Right.
Now, all these experiments, except this last one, was in gas phase, but most of the experiments they did before was in electrolysis with water. What happened in Fralick at NASA in 1989? This is a very interesting story. This is a picture of a gas purifier. This is a palladium tube where you enter dirty hydrogen, you heat it up, and then you produce clean hydrogen, because only hydrogen can pass through the palladium. So it's a very good filter for hydrogen. So that's a way to do pure hydrogen, a purifier. It's a hydrogen purifier, very well known. You can buy it on the shelf. That works. So this guy, Fralick, had a friend who had one of these purifiers. So he asked to loan it. So he borrowed it and loaded it with deuterium inside and outside of the system, and left it there for several weeks. He was waiting for neutrons, gamma rays, I mean, anything you can imagine due to a nuclear reaction. And nothing happened. No gamma rays, no neutrons, nothing. After a few weeks, his friend asked him to get the system back. So what he did, he pumped out the gases. And to his great surprise, temperature went up. And as you know, when you pump out, the temperature should go down and not up. So that was a really big surprise. So he wrote a report. There was a NASA report that was on their website for years. And now it's not there anymore, but it was there for many years. I have a copy of it, where he explains, if you're looking for neutrons and gamma rays, we have not seen anything, but we have seen excess heat, anomalous excess heat, because you should not get excess heat when you pump out. Recently, yeah.
And so the reason that palladium is partially transparent to hydrogen presumably has to do with geometry even at the nuclear level of both, one thing.
Well, more at the atomic level, let's say, not nuclear level, because it's between the atoms that the hydrogen will just find its way out, in and out in the system, you know?
Yeah, because we're saying that basically both hydrogen and palladium are dodecahedral conjugate, fractal, and recursive, so embeddability might apply.
That I don't know. Maybe you're right. So in 2011, many years later, he did the same experiment with a better measurement, you know. So he compared hydrogen and deuterium. So here you can see the loading of hydrogen. When it loads, temperature goes up. As you know, when you compress a gas, you increase the temperature, then it goes down. And when it pumps down, temperature goes down as normal. And that's always normal. This is all normal. But with deuterium, he has the same thing. Temperature goes up when he puts the pressure. The temperature goes up when he pumps out. This is absolutely abnormal. You should never see temperature going up when you pump out. You cannot have temperature up in both cases. So that was repeated many years after, again by Fradick himself at NASA. I don't know if he's now still working there, but he was there a few years ago. So I've done the same type of experiments myself. I've taken a tube, a palladium tube. Let me show you. This is a small palladium tube. I filled it with deuterium. I was heating it up with a wire. And these are just screens, reflectors for increasing the temperature inside. And I could measure with a mass flow calorimeter because I had designed my own mass flow calorimeter where I can put light water in and water out, so I can measure the heat flow. And I could measure excess heat that way. I'll show you here. This is the system I'm using. It's all handmade by myself. Not very good quality work, but anyway, that's my system. And this is the temperature. Well, part of the screen is, let's see. It's here. These are the watts. So I'm putting like 30 watts. This is power in, 30 watts constantly. And this is power out. So at the beginning, it's less than the power in because there are losses in my system, a few watts. But then it goes up. When I put the deuterium in it, it goes above the power in. And this is 1 day, 2 days, 3 days, 4 days, 5 days, 6 days. So you see, this experiment lasted for 6 days, and we could produce excess heat all the time, more than 10% excess heat constantly.
So again, this is deuterium reaction to palladium, right?
Yes, exactly. Same thing.
And presumably frequency and temperatures could be adjusted perhaps to optimize this energy out.
Absolutely. Yes. By changing the temperature, you change the flow rate. And actually, I have no real theory about it, but it seems that what's important is the flow rate, but also the amount of deuterium that is at the surface before they recombine. Maybe the reaction is occurring at the time of the recombination. I'm not sure. That's my guess. So it depends on the quality of the number of deuterium at the surface of the palladium when it comes out. It seems that it's happening when it comes out, not when it comes in, for some reason.
Again, some conjugate phonon frequency signature might dramatically increase the efficiency potentially.
Could be. In that case, I was just flowing hydrogen, deuterium in it. That's all. But maybe there are things to be done. Sure. Let me talk about photon conductors. This is my first experiment with cold fusion. I used aluminum lanthanum oxide. Aluminum lanthanum oxide is just like alumina, but now you replace one aluminum with one lanthanum, very similar. So normally it should be, if it was completely correct, without any vacancy, it should be white. But when the color is not very good because my camera is not very good, but anyway, when there are lanthanum vacancies in it, that means if you remove some of the lanthanum, then it becomes red. Now, if you heat it in hydrogen or deuterium, it becomes transparent. That means the hydrogen or the deuterium goes inside the vacancies of the lanthanum. So you replace one lanthanum by 3 hydrogen, because lanthanum has a valency of 3, hydrogen 1, so you can put 3 hydrogen inside one of the vacancies. So I have developed my calorimeter. I will not go too much into the details of that, but it's a heat flow calorimeter where I have a reaction cell here where I can put my samples in the middle. And here I have a number of 17 thermocouples. Here, 17 thermocouples there. Actually, no, that's a mistake. They should be here, actually. The thermocouple should be here. I made a mistake, the drawing. Anyway, so this is an insulator, and this is water. So when you measure the flow rate, the quantity of heat coming out of it, by calibration, you know exactly how much heat you produced. So I put my crystal here, lanthanum aluminum oxide crystal, and I measure the excess heat. And I measure the excess heat. Uh-oh, no, this is not good. The transfer of the files didn't work well. Let's see. Oh, no. Anyway, well, let me explain you. There was a calibration curve. You cannot see it here. But when I put I pass current through the crystal, I get more excess heat. Anyway, let's forget about the details of that.
You could zoom in on that. Yeah.
Yeah, but the black thing I gotta say, it's all black.
Oh, I see. That's an error. That's an error in the conversion from PowerPoint to PDF. Sorry.
Yeah, that's all right. I should have sent you a PDF. Maybe I can send you a PDF, but I don't know. It's too late. All right.
The point was that you did have excess heat.
Yeah, I had excess heat with that. Yes. It seemed that in vacancy, you have to. The idea is to have more than one deuterium in one vacancy. In palladium, it's difficult to do that because there's not much room. Because you see, if you have these atoms of palladium lined next to each other, there are small holes in between. It's hard to put more than one. With these vacancies of lanthanum, then you can put more than 3 inside because it's a big vacancy. This is the idea.
Mm-hmm. It's like a matrix.
Exactly. Arata, I told you about this double cathode electrode where he was using palladium powder. He did something very interesting. He produced nanoparticles of palladium inside zirconium oxide. Here it is. You see, this is the palladium. This is very small. This is, look at the scale, 100 angstrom. So it's very small. That is 10 nanometers. So a few nanometers, maybe 5 nanometer size. All these black dots are the palladium. And then this is zirconium oxide. And I will show you the experiment, how to do it. So what you do, you take an alloy of palladium and zirconium, you melt it, and you melt it on a cooled wheel. So it's called I don't call it. It's very fast cooling, so that the palladium and the zirconium don't have the time to crystallize. So you produce an amorphous layer of palladium and zirconium. Then you oxidize this layer, and you produce what I showed you before, that is zirconium oxide, because zirconium can be oxidized, but not the palladium. So you made a matrix so that the small grains of palladium get separated each from the other. They will not get close enough so they can melt and they stay apart. And you can load the palladium with deuterium. So what he did, Arata did that. In this picture. Oh, okay.
So that presumably something's happening, perhaps even at the atomic level, as it changes shape, basically.
So what's happening actually in that case, this is the work that there is a big project in Japan at the moment with Nissan, Toyota, and 4 universities working with this technology. They want to produce excess heat with this palladium zirconium oxide system, because then you can get excess heat with a solid and not at high temperature and not at low temperature like in electrochemistry, where you're limited by the boiling temperature of water. So you can go to high temperature with that. This is a major program in Japan on that. So there are other ways to do that. You can put palladium in zeolites. Zeolites are oxides with holes in it, vacancies, pretty large. So inside these vacancies, you can put small crystals, nanocrystals of palladium, and load them with hydrogen, deuterium afterwards. Kidwell at the Naval Research in NRL, Washington, he did that. He put palladium in zeolites, and then he put deuterium and hydrogen. Interestingly, when he put deuterium, you see a large peak. When he pumps out, he sees a smaller peak. Whereas with hydrogen, you see the same size peaks, hydrogen and hydrogen. So there is a difference between deuterium and hydrogen. Deuterium is producing heat when it puts inside, but not hydrogen. So again, in this case, you have nanoparticles of palladium inside zeolite, which is an oxide. Same thing as the other one with Arata, where he was using these nanoparticles of palladium inside zirconium oxide. So maybe the interface is very important. It's not only a problem with the material, but also of the interface.
Which is like surface area availability to react even at an atomic level. So when you tuck that palladium and deuterium into a lattice structure, it becomes more reactive.
Absolutely. This is very important. The surface is very important in that case. Not only a bulk system, the surface is important. So that's why you were talking about, what's his name? The beads, the palladium beads. The American guy, what was his name? Dan, you talked about in the beginning?
That's right, that Patterson.
Patterson was taking beads, kind of plastic beads, and he was putting layers of nickel, palladium, and nickel. So the interface was important, I think.
The layering.
Layering is important, yeah. And he couldn't reproduce it. He had a problem because the first batch he has worked, and then the other ones didn't work.
Exactly. And so that layering actually could be in a way alchemic or perfect packing or recursion or conjugate or fractal, the layering issue.
And again, remember the experiment with the multi-layers where he was transforming cesium into praseodymium? And the layers are important again. He has 5 layers. Without these layers, it doesn't work. The oxide is important. He has calcium oxide also. So the role of the oxide, the role of the layers are important.
You can think of the metaphor when you make phyllo dough for Greek pastry, the thin layers have a completely different taste. It's chemical availability.
Okay, the theories, maybe 60 theories about cold fusion. Some people talk about Bose-Einstein condensation. Some talk about electron screening. That means between 2 positive charges, if you put electrons in between, then they will be attracted instead of being repulsed. Hydrinos, that means some kind of shrinked hydrogen. Hydrotons, that means some change of hydrogens. Deep Dirac levels, that means the electrons if the electrons go to very high speed, their mass will increase and they will rotate closer to the nucleus, so maybe they will produce reactions after that. Neutrinos maybe are important. People talk about magnetic monopoles, gravitational potential, polyneutrons, ergions, all kinds of theories. Some are classical theories, some are just imagination, but anyway, many theories. What are the mechanisms? I talked at the beginning with a D plus D reaction, but maybe there are other reactions. You can imagine deuterium plus lithium-6. In their experiment, Pons and Fleischmann used lithium hydride, deuteride actually, for electrolysis. But you can imagine that lithium-6 plus deuterium produces barium-8. And barium-8 is unstable and will break into 2 helium-4, 2 alpha particles. So that's why we measure helium-4. It's not coming from the D, but coming from D plus Li6. Same thing with hydrogen and lithium-7. Again, produce barium-8 and 2 alpha particles. Or you can imagine also potassium-39 plus hydrogen producing calcium-40. So there are many other possible reactions with other metals. And still open, the jury's out. We don't know. We have no solution yet to all that.
I mean, if you think of what a fusion reaction must mean in terms of the cloud charge or plasma, that the hydrogen atom being a single proton, if you visualize it toroidally, for it to embed in a heavier atom, it has to nest, and the layers of the cloud of charge of hydrogen, which my new equation proved, the radii of hydrogen are golden ratio, which is embeddability perfected, which is a clue to the hydrogen availability to react even at a nuclear level for fusion. So it's literally, if you realize what we're calling an atom is a cloud of charge, and for them to nest or embed or fuse, they have to get centripetal to a common center. So that means that there are field effects that could catalyze this as well.
Anyway, just to conclude, so the scientific demonstration of the existence of cold fusion has been made many years ago. I mean, a couple of years after discovery, all the proof of the existence of cold fusion was there. Nobody wanted to look at it, but it was there. At the beginning, people were working maybe with electrochemistry because that was easier. But now the focus is more on gas phase experiments because it's more convenient to do to get to high temperatures. You know that palladium melts at 1,553 degrees C. So it's much easier to do energy with that temperature than with boiling water. Now, nano powders are probably the solution for industrial applications because nano powders have a different behavior as the massive material, the bulk materials. So people are more interested with nano powders now. And I've done my own experiments with nano powders, and nano powders of nickel loads very well, whereas solid nickel don't load at all. So there are many chances that the future will be in nano powders, you know.
And nanomaterials become stable electrically only in certain geometries and only in certain electric fields. So to get it stable at a molecular level, when the nanoparticle is so small, even single atom requires certain field effect catalysis. For example, how carbon nano is made, and carbon nano has many implications here as well. So basically, to be a nano and stable enables you then to get the availability to react at nuclear level.
Now you have my picture again.
Oh yes. No, your camera for some reason. We're sorry we lost Jean-Paul's picture here.
Okay. You see me or not? That's okay.
No,
if you don't see me, it's not a problem. Forget it.
So sorry. Sorry, Jean-Paul.
So I'm done about the presentation. If people have questions, I'm very open to questions.
It's wonderful that you took the time to try to make this available to the general public and to make this shareable. There was one quick question from Michael P. in the chat window. Did you have any? He was interested in information about isotopes of cobalt. Were they involved in any of these fusion reactions? You know what?
I think very good. Cobalt is a very good material. I would love to work with cobalt because cobalt is ferromagnetic. So, but nobody has worked with cobalt so far, to my knowledge. Nobody worked with cobalt. People have worked with palladium, titanium, nickel. That's about all. Most people didn't work with other materials. There are many other things to be done. And nobody knows anything about at this point.
And I wonder, just a quick thought here. My work has been on the electric fields that create negentropy or self-organization. Would you call any of these kind of fusion reactions negentropic in the sense of increased order? Would that be appropriate?
That's appropriate, yes, because you have two particles, then you have only one, so you have probably improved the entropy that way, true, yeah.
Yeah, and that part of the evidence was you didn't get as much gamma as you expected, meaning they weren't breaking up to disorder, they may be increasing order. So that we're working on all kinds of theories about increased order, including phase conjugate and plasma. In fact, we even brought our phase conjugate Therify plasma system over to test the results at Jean-Paul's, and we got a very preliminary indication of some increase in heat, and we hope to replicate and tune that a bit. But the theory would be that optimized frequency signatures could help this idea of fusion by electrical fields. So Jean-Paul, just thank you again for your patience with us and for sharing with us. Jean-Paul is an immense resource on fusion research. He's very available on his websites. Let's conclude, also put your websites in here, Jean-Paul. It's cryofusion.org, right?
Yes, that's right. Can I write it down?
Yes, cryofusion.org. You see the chat window, did I get that right? Maybe I spelled that right.
Okay.
Cryofusion.org and jeanpaulbiberian.net. And yes, cryofusion.org, correct the spelling, and your personal website, jeanpaulbiberian.net. And Jean-Paul put his contact information at the opening slide. Yes, thank you. So there's the websites there. And so for those who are dreaming about alchemy and implosive charge collapse, here is a taste of the physics. And we're so grateful that Jean-Paul has been so available to connect with us and make this sharing. We know that you have to go off and pick up your magic lady, Jean-Paul. Thank you so much.
Thank you.
Yes.
One last thing, you know, this field has been going on for 29 years, but now we are close to application. So that will be very important for the future. I mean, we are at the edge of a major revolution in the energy in the world, you know, worldwide. So
that's the point. That's the good part. That you know, although the field has been ignored for a long time, the time is coming now that not only is it needed badly, but it's actually becoming available thanks to people like Jean-Paul Biberian. You're our hero. Thank you, Jean-Paul.
Okay. If people want to talk to me, they can send me emails. There's no problem. My email, I can give it again here so people will know.
Yes, Jean-Paul is available on email. Blessings. Thanks, everybody. Thank you, Jean-Paul. Blessings. See you next week. Okay. Bye-bye.
Thank you very much. Bye-bye. Yes.
There's his email. Thank you, Jean-Paul. Bye-bye.
Bye-bye, everybody. Thank you again.
Bye, everybody.
Bye.